Let me get down a little bit into the architecture now. All these things are going to be on the theme of how we're delivering consistent and predictable performance, and also ease of use in the system. At a high level, everything that we developed is XtremIO intellectual property. So we didn't use like open source stuff that we found out there. It's not things that once we got acquired, we started adopting like deduplication algorithms from inside of EMC. Everything was developed from the ground up, specific to XtremIO. I will describe things in kind of a simplified fashion. We're built on layers that interact with each other. I'll tend to talk about them as if they're independent so that it's a little more clear. But each layer does serve multiple functions. So the first thing we have is that at the core of our system we run a Linux kernel. But if you were able to, as an admin, log in at the Linux layer in our system and look, you would see that the CPU and the memory is always 100% utilized. And the reason is because we have our own user space operating system that we wrote that sits on top of Linux, grabs control over all the cores and all of the memory the second it boots. And then all of the user space processes that run in XtremIO are sitting on top of this XIOS operating system. And we did this for a very good reason. It's because the controllers that we have are multi-socket, multi-core. So if you look inside a controller, we've got 2 sockets. We today have 8 cores per socket. And so we instantiate an instance of XIOS on each. And we do this because we don't want to have inter-socket sync, and we want to avoid inter-core sync. These are all things that throw interrupts in the hardware, and it makes things unpredictable in terms of what latency profile you're going to get. So the whole purpose of the XIOS operating system is so that we can control where we're going to allocate every thread and make sure that processes that need to be on the same core can be on the same core. And so this is one of the reasons why we're able to run huge parallelism of thread counts on the system and to maintain consistent and predictable performance. Now, what we do inside those user space processes on XIOS is very unique. We do a content addressing method of locating where data is going to reside in the array. And this is very important. It gives us 2 big benefits in the system. One is that it randomizes the locations of where the data is going to go. The other one is that it gives us a method of finding matches in the data stream. So it becomes the basis for deduplication. Deduplication on XtremIO isn't a separate process that runs. It's a byproduct. It's something we get for free as something that we're doing in content addressing. And so if you imagine a host writing data to an XtremIO array coming in here on the left, what we do is at a very fine granularity, we segment the incoming data stream into small blocks. And for every block, we calculate a fingerprint of the unique contents inside that block. Or in this case, we're the ones, the colors here denote whether it's unique or not. These 2 ones that are in blue have the same contents. You wind up with the same fingerprint. And the algorithm that we use to do this generates fingerprints that if the data is not an exact match, the fingerprints will look like random numbers. So I can have 2 chunks of data that are different by 1 bit, but the fingerprints won't correlate in any way. So we leverage the randomness of these fingerprint values to randomly disperse data across the cluster and achieve even resource utilization. It's the exact opposite of what you would have done in the world of disk. In disk, you're trying to take things that are random and sequentialize them so that you avoid seeking the heads on the drives. We're taking things, even if they were sequential, and randomly dispersing them so that we can achieve balanced resource utilization in a scale-out cluster.
So what happens when you delete data? How do you keep it balanced?
Oh, so statistically, data is already going to be dispersed across everything, and statistically, if you delete things, those fingerprints that you're deleting are also going to be statistically diverse. So remember, you could delete something that has a pattern to it, but the fingerprints that describe that are going to have no pattern to it. So you automatically are freeing up even space on all the different nodes and all the different SSDs. I'll show you some data about this from one of our production arrays, and it's amazing how well this works.
What are the block sizes that you're dispersing amongst?
It's only a few kilobytes in size. So taking it a little bit further down, if we had a 2-brick cluster, so we have 4 controllers, then the way we would look to disperse data is imagine that we have, these fingerprints are hex numbers. We have 16 possible values they could start with. We can divide that address space up among the 4 controllers, so each one has a quarter of it. And now you can think about how things would get mapped. This block that starts with C would be handled by the controller over here. This block that starts with F would be handled by this controller over here. And the data inherently starts to balance itself. So one of the things about an XtremIO system is that we're not picking up data in the background and trying to move it around to keep the cluster balanced over time as people are writing information. Everything is balanced the second it's written. There's only two situations where we would ever pick something up and relocate it. One would be if you had an SSD that failed, so we don't rebuild to one other SSD, we would disperse the data to a new location during the rebuild. The other one would be in the situation you were asking about, which would be when you expand a cluster, we would rebalance it.
How do you handle different block sizes of incoming data?
So anything that comes in is still segmented into just a few kilobytes in size each, fingerprinted, and then dispersed across the cluster in smaller chunk sizes. So the array can handle any block size that's coming in, but what we're doing internally with it is moving it around in uniform sizes underneath. You notice this last block up here hasn't been written. So this is what we do as kind of the second part of this process. Every time we calculate one of these fingerprints, we also track it as part of our metadata. So anytime we see a fingerprint come in, we will look up and see if we have that fingerprint on the array somewhere already. In this case, we do. It's down here. And so we don't need to write the block a second time. So this is kind of the byproduct of doing content addressing, is that we can do inline deduplication of the data. So it's interesting because people classically would think about deduplication as something that's going to slow down the array. In our case, it's something we're getting for free, and the array will actually run faster when there's duplicates in the data stream. So if we have to write 100% unique writes, all unique data, then everything's getting committed to flash. And that's the worst case scenario for XtremIO. That's also the way we spec our systems. So we give you the worst case numbers. If you have duplicates in the data stream, at this point there's nothing to write to flash. We just create a metadata pointer to the existing block. That's a faster process than committing to flash. And so the array picks up performance when there's duplicates in the data stream.
What's the latency from receive to identify to commit writes to check metadata? Like, I know it's very small, but I mean, there's obviously eventual consistency hiding behind that at some point with transactions, because you can't have this big long queue of waiting for the metadata response.
Yeah, the array is typically running sub-millisecond, and depending on the load, of course. Like any storage array, the more load you're pushing on it, the higher the latency is going to get. We would spec, again, our performance would be, what we would spec is like 150,000 IOPS with a mixed 50-50 read-write ratio, and that would be all sub-millisecond. And as we scale, that'll just keep going up. So it can go to 300,000, 600,000, 900,000 IOs. The cool thing is that everything in the system is completely balanced. You get all this performance without having to think about how to do any kind of setup or tuning to drive it. So on XtremIO, there's really only 3 steps to set up storage. You create a volume, give it a name and a capacity, you create your initiator group, and then you just map what's going to talk to what. That's it. There's no RAID levels, there's no how many drives go into a RAID group, there's no stripe sizes, there's no cache policies, no tiering policies, nothing. It's one screen with 3 steps.
So how do you make sure the distribution is even across all the nodes?
So again, the content addressing that we're doing statistically is going to do that.
Okay.
Because those fingerprints are random and uncorrelated to each other, then statistically you get a uniform distribution across all the nodes and all the underlying SSDs.
But you don't have any mechanism to actually ensure the even distribution other than what you just told?
Oh no, we can look, and I'll actually show you the next slide. Okay. We'll show you that, and it's very perfect. We track it. So this is in our UI. You can actually set up to look at the CPU utilization across the different controllers. You can see here we have a 4-node cluster, and everything is evenly balanced. We have processes that handle data processing as well as metadata. This is to your question. Here we're looking at that same 2-brick cluster. There's 50 SSDs, so they're numbered 1 through 50 over here. And if you look at this chart for a second, you would say, wow, this doesn't look very balanced, right? This line's a lot smaller than that line. But I am zoomed in at an incredible scale here. So these are systems where the array's almost 80% full. Every SSD has about 250 gigabytes written to it. And you look at the variation here from the least filled drive to the most filled drive, it's only 0.1%. And statistically, what will happen if I took a snapshot a little bit later in time is this one would tend to come up, this one would, it all is staying balanced. So there's fine amounts of variation statistically, but it always stays globally balanced.
What's the goal for utilization as far as data on disk and what happens when you blow
as you
past
fill
that?
up? So we don't need to reserve any space. So when we present, like in this case, 14.9 terabytes usable to the user, you want to fill that up 100%, it's fine. In fact, this is something that we tell customers to POC when they're trying the system because we're very unique in this respect. Everybody else out there has some limit where they say, don't run our array past 80% full, don't run it past 70% full, because the performance will fall down, the array can no longer find those full stripes, the garbage collection's kicking in. We have really licked that problem, and so customers can run these things at incredible levels of utilization. All right, so we kind of covered this, so I'm going to skip over it a little bit, but this is the one screen in our system where you set things up. So you have a pane over here where you create your volume, a name and a size. You have a screen here where you click a button and you discover your initiators on the SAN. And then in the middle here, you just map them to each other. That's all you ever do on an XtremIO array. It's a piece of cake to run it and manage it. The other benefit of having this completely balanced architecture, it's not just around performance and simplicity, it's around the endurance of the flash media. So we cannot hotspot our array, we cannot burn out one SSD by having some I/O pattern that's going to keep hammering it because, again, statistically everything gets distributed. The classic hotspot use case is in a database. Somebody writes a SQL statement and it keeps updating a record in the database that maps to some location in the array, and then you just hammer that one part of the array. If that happened on XtremIO, every time that update happened, the content would change, the fingerprint would change, the location where that I/O gets directed would change as well. So everything stays balanced. It cannot get hot-spotted. And you can see that here. So we're looking at a system that had been in our QA lab where we purposely were saturating it. And so it had been in for about 9 months. We had written over 6 petabytes to the array. So that's over 242 terabytes per SSD. And you look at the endurance remaining on each drive, and we had only hit 2% wear across the board. And this is with MLC. So we don't need to go to expensive SLC flash in order to do this. And it's exactly balanced across all the SSDs.
Now, we talk about that all the time, like that failure scenario of the actual SSD going sideways on us, but the statistical chance of having that happen versus the latency required to continuously redistribute data, is there, what was the choice to weigh that out? Have you actually seen, mean time between failure has actually proven that you needed to continually redistribute?
Yeah, the failure rates on the SSDs are unbelievably low. Much, much more reliable than mechanical drives for sure. And I think in the entire population of XtremIO systems in the field now, which is tens of thousands of SSDs, there's been like 6. So they're very reliable devices. And when they do fail, it tends to be infant mortality. So it's some manufacturing defect as opposed to like it's been running for months and something goes crazy.
Do you have some sort of predictive can you predict the fails? Because some of your competitors can predict when the disk will fail.
Sure.
There is count on...
Yeah, so on predictive failure, the SSDs all have smart counters, and so the array can monitor that. We know if the SSD is starting to use lots of spare flash in it for things like that. Frankly, nothing's happens. These things have been in production and getting pounded now for quite a while, and we never see anything predicting a failure in any kind of reasonable lifetime for the array. So the first array that we have in the field with a customer, it's been out there now for about 9 or 10 months, hit 1% wear on the SSDs, meaning 99% of the endurance is still remaining. And this was after they had written 35, it's a 10 terabyte brick, just a single basic starter system. They were writing 35 terabytes of unique data per day to that 10 terabyte system. So just cycling it over and over and over again for about 7, 8, 9 months, and then all of that write data finally clicked over to 1% wear on all the SSDs at the same time. We then had another array do it a couple of days later after 2.6 petabytes of host writes had been written to it, again, a single 10 terabyte brick. So the bottom line is that endurance is completely off the table as a concern on XtremIO arrays. You will never in the lifetime of the array have an endurance related concern. So much so that we actually warrant it, so that we warrant the drives now for 7 years against any kind of endurance failure. And other people are doing this too. The difference with us is that what other people are doing is they're saying, hey, when you have an endurance-related failure, we'll replace the drive for free. We do that, but we're also telling you you're never going to have to get to that state. You're not going to have to deal with somebody coming out to replace the drive. You're not going to have to deal with the rebuild. You're not going to have to deal with the risk of something else going wrong during the rebuild. So it's a much stronger statement, I think, about what we're going to do with endurance.
I'm curious, the 7 years maintenance protection is about the fixed price that you give at the beginning, and the price remains the same for 7 years?
That's exactly right. So yeah, so we don't do the thing that you would normally see in the industry, which is, you know, after a few years of maintenance, the price goes way up. We're locking in your original maintenance cost for a full 7 years. So again, the data that we have coming in from the field on the reliability of the arrays is tremendous, and it allows us to do these kinds of things.
In a case where, say, you start out with a single brick, you light up your 7 years, 2 years in, you double down, another year in, you purchase a third. Are you then continuing the 7 years out of the third purchase, or is it
like
all
whether it's coterm or not?
Right.
I think it is coterm, but I don't want to answer definitively because I don't know all the rules and regulations there.